The first talk today will be by Professor Enrique Iglesia, and he will be speaking on structural evolution and site requirements for Fischer-Tropsch synthesis catalysts based on iron oxide precursors, promoted with copper, ruthenium, or potassium.
Thank you. Okay, well, for those of you that were listening to me this morning, you know I didn't mention iron once, and that's because I wanted to save all the punchlines for the afternoon and talk today about iron-based catalysts. Now, I have to admit to you that if I had seen a talk with this title in this meeting, I would have never shown up for the talk, because you probably have heard 45 talks over the years that effectively try to say the same thing. How does iron change and what is the active site? I think that you did the right thing by being here, because I want to tell you something different. I'm going to give you an approach that I think has been seldom taken with this particular materials. As we know, one of the problems with iron catalysts is that you begin with a precursor, and that precursor actually during reaction transforms into whatever it is that may be active for Fischer-Tropsch synthesis. And that in contrast with cobalt, we seem to have not only the active component, but the structural promoter, the metal oxide, and things that have been at various points misconstrued as either chemical or structural promoters of iron-based catalysts. During the reaction, this changes, and there are some things that are clear. There are some things that happen and we know happen, and that is that copper reduces in this particular material, that a zinc ferrite phase that we have in the system does not do anything except stay as such, that the potassium is as potassium carbonate, and we know all this from doing X-ray absorption during reaction. But finally, we know that in the process of running this catalyst from time equals 0 to some finite time, there are significant changes in the composition of the iron phases that you make. And my talk today is going to attempt to answer the following questions. Attempt is going to be the right verb to use, because I'm not sure that the questions can be answered. That's going to be one of my messages. What are the nature of the active sites, and what sort of structures you have there in a dynamic sense during the reaction? What do the promoters do, and can we actually measure the density of active sites that we have in the material? We're going to take a conventional approach of looking at what they do under steady-state Fischer-Tropsch conditions. We're going to take two less conventional approaches. One of them is to actually look at the initial transients and look at the details of a product, of a complex product distribution with a resolution of about 1 second using online mass spectrometry and a deconvolution of complex mass spectra. We're also going to look at the material as it works. We're going to build a little plug flow reactor in the form of a capillary. We're going to take it over to the synchrotron, and we're actually going to do X-ray absorption around the iron edge while the reaction takes place, all the way from the beginning precursors to something that looks like steady state. And finally, I'm going to show you about a somewhat imperfect, but nonetheless reasonable technique that begins to tell you something about how to measure the number of sites actually on an activated catalyst, not in your starting precursors, which by definition do not have the active sites that you're going to need to carry out this reaction. Well, the first technique is quite simple. You run the catalyst in helium at the temperature that you want, and you introduce a chemical transient. You bring in hydrogen and CO, and you follow the evolution of the products as a function of time. The other one is you take your reactor and you put it inside a wall-control atmosphere where you can go up to about 10 atmospheres and about 600 degrees, not that we ever want to do that with one of these catalysts. You run your gases through there, you put an X-ray beam through it, and you try to get a spectrum near the K edge of iron, which for those of you that are not familiar with X-ray absorption, you do not need to know how it works in order to understand what I'm going to tell you, but it's the region near the edge where we can get a lot of information about the local coordination and the oxidation state of the material. What we do with that is we actually attempt to fit it as a linear combination of compounds, the structure of which we know. For example, the starting material, Fe2O3, Fe3O4, the known forms of iron carbide and iron metal. As a result of that experiment comes a percent of the sample that is present during reaction, as the reaction takes place, as each one of those standard compounds. Let's begin with the isothermal transients, in which we introduce that chemical transient. What we're going to do is again, at time equals 0 in this scale, I'm going to switch from helium to hydrogen and CO, and I'm going to watch the evolution of methane as a surrogate product of hydrocarbon synthesis. I'm not going to look at every product. I'm going to treat methane and say, I can tell roughly what is going on from methane because the selectivity turns out doesn't change very much as we activate the catalyst. Notice that for iron oxide, without any promoters there is an induction period. If you now look at the products that carry the oxygen away from the starting Fe2O3, what you find is that water and CO2 are made in a large excess over what would be predicted by the reaction of methane formation and hydrocarbon formation, okay? And the CO2 and the water are made in this period of time in much higher quantities than what you would make at steady state. In other words, the bottom line is that there is a net removal of oxygen from the sample, and that net removal gives rise to the appearance of catalytic activity. What is surprising about this net removal is, first of all, that it occurs very rapidly. The second thing that is interesting is that the amounts that are removed are of order a monolayer of oxygen, and that by the time you remove something of that order, you actually have something that looks like steady-state activity for this sample. Well, what is the role of promoters? We all know that when we put copper, for example, or potassium for that matter, in these samples, two things happen. One of them is the induction period becomes shorter. Copper is able to aid in the activation and the removal of this oxygen, presumably by activating hydrogen, for example, which then removes some of that oxygen. If you now look at the oxygen-containing samples containing products here, the water and the CO2, you find out that the amount that is removed, the total amount, is really not very different. The activity is higher and the induction period is shorter. And also in this case, the total amount of oxygen that is removed in order to generate this higher steady-state activity is actually of order a monolayer. And of order a monolayer means really that, of order a monolayer, 10 to the 19th or so per meter square. Okay, if you look at the amount of methane formation, again, this is nothing more than the details of what I showed you before. Here's the reduction of copper, here's the removal of oxygen, and here's the appearance of catalytic activity. Here is the change in the induction period. What I want to do is I want to couple this experiment, and in the same time scale in which I'm doing the evolution of the product analysis, I'm going to do an X-ray absorption experiment. I'm going to do it first in Fe2O3, and I'm going to look at what happens as a function of short times here. This is of the order of seconds. Here is the starting Fe2O3 material being consumed. Here's the Fe3O4 and the iron carbide. By the way, X-ray absorption cannot tell me which iron carbide I have made, because the three most likely structures have near-edge features that are almost identical. So all I can tell you, it is not Fe3O4, it's a carbide of some sort. Well, you immediately look at this and say, the active site for this reaction is Fe3O4. But then you say, no, because at the same time as the activity is appearing, I'm also making the iron carbide. The fact that these two are increasing in parallel means that from this experiment, you cannot really tell which one of the two is providing the active structure. What you can tell is it only takes a very small amount, a near-surface region rearrangement in order to get to that steady state, and the time that is required and the rate that you obtain actually depends on the presence of that promoter. If you do the same thing now on a copper-promoted sample, what you find is that indeed the induction period is now quite a bit shorter, but again here there is the appearance of catalytic activity at the same time as both of those structures are concurrently increasing in concentration. So you're left with yet another inconclusive experiment as to whether it's the oxide or the carbide that is active for the reaction, but you're left with one important conclusion, and that is that after you have done whatever needs to be done to the surface, that surface acts almost independently of what may lie in the bulk of the crystallite. Because I have large amounts of Fe2O3, and yet the catalytic rate of this reaction had reached a pseudo-steady state type rate. I just wanted to put this one up, although I'm not going to discuss it in details because it's a little bit more complicated, but I wanted to show you that directionally the effect of potassium is the same. The effect of potassium is to decrease the induction period even more than what you get with copper, is to actually give you a higher rate This is an order of magnitude larger scale than that one, but to show some behavior near the beginning where the steady state is reached only by an overshoot and an undershoot. And I don't want to talk about the details of that one here today. Let me summarize what I think is important up to this point. A small amount of oxygen has to be removed. It is removed early on, and you don't need to remove very much in order to reach the steady state catalytic behavior. That is enough to cause at least the onset of that steady state behavior. The bulk is largely unconverted. What is in the bulk is not critical to the behavior of those near surface layers. Now, the presumed definitive experiment is going to be to pre-make well-defined structures of Fe3O4 and Fe2 and iron carbide and look at their catalytic behavior in a transient mode. Do they activate during the reaction? Is one of them more active than the other one? And the way that we're going to do that is we're going to look very carefully at the reduction of Fe2O3 in hydrogen and interrupt that reduction when we need to when we get to Fe2O3. We're going to do that in a copper-containing sample because it is easier to separate the subsequent reduction, which we're not interested in. And actually, if you do the same experiment now in CO, you appear to be able to also stop the reaction after the formation of a carbide and without the formation of this extra carbon that is actually due to the boudoir reaction. So we're going to interrupt the carburization at this point. And now what we're going to do is we're going to do transient experiments using both Fe3O4 and this iron carbide at the starting material. Let's do it first with Fe3O4. If you start with Fe3O4, you actually get an induction period that is shorter. That means that Fe3O4 is enough to give you the catalytic activity that you want. There is no induction period. And actually, if you look at the removal of the oxygen, there's very, very little oxygen that needs to be removed from Fe3O4 in order to make it active. This is an order of magnitude lower than what we had before as far as oxygen removal, 2 orders of magnitude. The conclusion, therefore, is that Fe3O4 is the active phase of the reaction. The conclusion is, however, flawed. It is flawed because if I do the other experiment, if I take now a pre-made iron carbide and I put it through the same paces, and I do an isothermal transient, that the iron carbide also does not have an induction period. It also doesn't have the need to either accept or remove any oxygen in order to become catalytically active, and it becomes catalytically active with almost the same activity at that Fe3O4. Why is it that we cannot tell which one is the active site? Because apparently, within times that are of order of a turnover time, you can interconvert in the near surface layers the carbide and an oxide. Near turnover times means that what we're doing is part of the chemical reaction. That this chemical reaction is taking place on a surface layer, on a near surface structure that is dynamically responding to what you have in the gas phase, and therefore the question of whether it's a carbide or an oxide that is active for the reaction is not one that we can even attempt to answer here. The transformation is part of the catalytic reaction itself. They interconvert so rapidly that these kinds of conclusions are going to be intrinsically equivocal. It has nothing to do with how much you try. It has to do with the fact that the chemistry that transforms the two is the same chemistry that is activating CO, forming a carbon and an oxygen, and then removing those in order to complete a turnover. What makes this problem all the more difficult is the fact that what you have in the bulk appears to be irrelevant. And as a result of it, the bulk characterization techniques that we use are going to give you, again, distracting and misleading results. Nonetheless, the story is not as, perhaps as sad as I make it sound. Let me continue and try to give you a little bit more information about the system. What I've done here is I have shown you now the in situ X-ray absorption experiment on 2 samples, a potassium and a potassium ruthenium. I put the ruthenium here because the data is a little bit more detailed. Think of ruthenium in much the same way as you do about copper. It effectively does the same kind of thing. What I'd like to point out here is that this is over much longer periods of time. Okay? The reaction has reached steady state here, but there is a continuous increase in the amount of carbide that you have in the system, even after you have reached steady state. this doesn't mean that the carbide is the active phase. It means that thermodynamically it's more stable on the oxide, and therefore, as diffusion into the bulk becomes available, you're able to transform the oxide into the more stable thermodynamic phase. However, if I look at this catalyst right here, it has a steady state concentration of carbide, which is of order 20% or so. If I look at this one, which is a significantly more active catalyst, this is about 60% or so. So if I look blindly at this data, I would say there is a correlation between the rate of the reaction and the amount of carbide that you have there. Therefore, incorrectly, I conclude by this in situ experiment that the carbide is the active phase. Now, mind you, the X-ray absorption experiments, for reasons that I don't understand, had never been done on iron-based catalysts and never been done at reaction conditions. And therefore, this data were not available to make that conclusion. This is the amount of carbide that you have at steady state, and this is the rate of the catalytic reaction. Anybody looking for structural functional relationships here would conclude that the carbide is the active phase. They wouldn't conclude that they can't tell, which is effectively the correct conclusion. However, this is puzzling for another reason. Okay, first, this is the same kind of data, a little bit larger. Okay, again, an increase in rate, an increase in the amount of carbide for, here I include the copper and the ruthenium, both of them, before I just show you those two. Okay, let's look at this for a moment and try to make the point one more time. This is the methane synthesis rate, the methane formation rate versus time during the initial transit. This is for potassium, copper, and by the way, these are the atomic fractions of each one of the promoters that we have there. There's an increase as you go from no metal to copper to ruthenium. There is an increase in the steady state concentration of the carbide. But what is misleading about this plot, and what I show you here, is that this entire time is compressed right there. These systems are continuing to carbide without any catalytic consequences in a way that somehow coincidentally matches the fact that the more active catalyst is more easy to carbide. So if the bulk structure doesn't matter, why does the extent of carburization and the rate of the reaction seem to increase in parallel? I'm going to imply that there's no causal relationship between the two, that the two are actually reflecting something about this system that is giving rise to both the higher catalytic activity and the easier transformation to the carbide. Okay, a summary, not that is necessary, but nonetheless to get everybody in the same page. We need only the surface, and we need some reduction in order to reach steady state rate. The interconversion between the two is effectively so rapid that we cannot tell which one of the two may actually be involved in the reaction. And the promoters that increase the rate also increase the extent of bulk carburization. I'm going to borrow from what is known in the area of oxide to carbide transformations to make the following proposal. That the role of the promoters, which I have here as these little blue dots in a very schematic, and nobody please hold me to this picture, what they're doing is that they're providing nucleation sites for the reduction. In other words, that reduction will begin preferentially near there because those sites can activate either the CO or the hydrogen. Once you do that, you're going to get a faster rate of carburization, of reduction, and that's what we see when we have the promoters there. You're also going to get a higher rate of reaction, I claim, because in the process of doing that, the more nucleation sites that you have, the smaller the crystallites that you're going to end up at the end of this exercise. This is well known in nucleation and growth. You have to eat up all your nutrients in a given number of nuclei. The more nuclei you have, the smaller they're going to be when they become crystallites. Now notice what the consequence of this proposal is. It is that the reason why it's easier to carburize is because you have a shorter bulk diffusion distance. In other words, if you have smaller crystallites, you have less distance to go in order to remove the bulk and catalytically irrelevant oxygen and get it to the surface so that you can remove it and reduce now the bulk of the sample. So that what we're going to find is that this will increase the number of nucleation sites. It will give you a higher surface area of whatever the thermodynamically stable phase may be, with whatever on the surface wants to be there in dynamic steady state with the gas phase, and that you will get both a higher rate, a higher surface area, and a larger number of sites. In other words, the small crystallites are what are causing both the easier carburization and the higher rate. The higher extent of carburization is not what is giving you the higher rate. Okay, I want to borrow also from the work of the Daphnia Group, in which they have looked at the conversion, or they have looked at the aftermath of the conversion of an iron oxide into an iron carbide, and have detected effectively something that doesn't look like a shrinking core model, but actually one of these pimply surfaces that I showed you earlier. And their scheme for how this happens, which has some of the components of the one that I'm proposing to you today, effectively takes a starting material with holes. Ours doesn't really have these holes. The formation of carbide, and then effectively the eating up of all the oxide by continuing to grow those carbide species. Okay? In some of the details is similar to what we propose, in others it's not, in that in this case the surface area of the carbide is actually increasing with time. So you would have to see an increase in the rate of the reaction that we do not see. Okay. Let me show you now that indeed what I told you was happening. If I take the rate of the reaction on these three samples, potassium, potassium copper, and potassium ruthenium, those are the rates. If I carry out the activation of the reaction for 1 hour in hydrogen and CO, and I quench the reaction and I passivate the sample, and then I measure the BET surface area of the sample, it is indeed higher when I have a promoter there. I can't let it go too long, because then I begin to build wax and it becomes impossible to do that measure. The more difficult measurement is this one. I'm going to quench the reaction, and I'm not going to passivate. I'm going to leave it in the reactor, and I'm going to heat the sample up in helium in order to attempt to desorb CO and CO2. And when I do that on this free catalyst, I actually get something that looks like that. There is a problem with that experiment, however, and that is that what you're measuring, or at least part of what you're measuring, is carbon that is on the surface, that is reacting with oxygen that is still in the bulk, and that is diffusing at these very high temperatures. So it turns out this is why this experiment cannot work. However, if at the end of the reaction you absorb CO on that surface, and you repeat the experiment again, in other words, rather than heating up in helium, before you heat up in helium, absorb some CO. Then desorb the CO that you put on the surface, and desorb all the other carbon that came off before you put the CO there. Take the difference between the two, and you actually can calculate the amount of CO that you have placed on that surface as a result of the chemosorption measure. It's not a trivial experiment, but we couldn't think of any other thing to do. And what I show you here is that indeed, when you look at that CO chemosorb, which is the difference between these two, you actually also get an increase as you put the promoters that are giving you the higher activity and the higher surface area. So what you have made is you have made a higher surface area material. Copper and potassium are acting to form a larger surface area, a smaller set of particles of what ends up being the in situ form active structure. Well, now let's take this and let's see what we can do to make a higher surface area material. Because at the end of my talk, I have told you almost everything that I wanted to tell you about what you can and cannot know about these materials. I'm going to tell you now what you could do to try to improve further the catalytic activity of this material. Because at the end of my talk, I want to leave you with an iron catalyst that is actually good enough to put next to a cobalt catalyst and say these catalysts are just as active as the other. What I'm going to do is I'm going to take the traditional method of co-precipitating iron catalyst, and we have detected that during the drying of those materials, there's quite a bit of pore collapse as a result of the removal of a high surface tension liquid like water. So what we have done is we have added a surface active component that decreases the surface tension of water, and we have then done the drying to effectively increase the surface area of those materials by about 50%. The question is, when you do that, and then you pre-treat it at a temperature that preserves some of that surface area, what do you find? But what you find is that the catalyst that one makes by starting with a higher surface area precursor, this is the rate of hydrocarbon synthesis, this is the conversion, and it is about 2 times as active as the one with a lower surface area. Again, there is a preservation of that surface area that you have put in there, and still the effects of the promoter. Now notice how I put twice the amount of the promoter there. It's twice the surface area. The relevant variable in promoting these materials we have found is not the atomic fraction, but the number of atoms of promoters that you put per unit surface area. Well, this is a summary of two samples. A sample made by the alcohol wash method, a sample made by the normal water wash. Here is the higher rate of the reaction. Here is the higher surface area. Here is the larger amount of CO can absorb. And here again, without implying in any way that that is the active phase, here's a catalyst that is able to convert to the carbide more fully because it has, again, a shorter diffusion distance in order to remove that oxygen. And you can only get this if you keep not the concentration of the promoter, but the surface density constant. In other words, if we had put 2 and 1 here, as we did here, we would have gotten much inferior behavior. And the reason for that is that for the higher surface area, you would not proportionally increase the number of nucleation sites if you don't proportionally increase the amount of the promoters that are doing that nucleation for you. Okay. I said I was going to make a comment about the fact that we have fallen in love with cobalt catalysts and forgotten that there's such things as iron catalysts that also do Fischer-Tropsch. And one of the arguments, two of the arguments that are made against iron catalysts are that they're not as active as cobalt and that they make CO2. Only one of those two remains an issue. If I look at the catalyst that we have prepared here, and if I do it on a turnover rate basis, and mind you, here, you need a measure of the number of active sites, and we're going to use the CO double titration method that I just described for you. On a per site basis, cobalt is more active. Notice that this is at cobalt-like conditions, where most of us would not dare run an iron catalyst. 200 degrees, 2-to-1 hydrogen to CO ratio, 20 atmospheres. If I compare that now to a cobalt catalyst here, what I find is that the productivity on a per weight basis is about the same, and the productivity on a per volume basis is actually lower on this cobalt catalyst. The selectivity to methane is much lower. The olefin selectivity in the C2 to C4 is much higher here, but even at these low temperatures, iron-based catalysts are also making a significant amount of CO2, and that remains an issue that is not removed by lowering the temperature, increasing the activity of the sample. Now, you should argue about the fact that I gave you a cobalt silica catalyst of my making, and I'm pretty good at making cobalt silica catalysts, but nonetheless, let's take one of the best catalysts in the literature. This is one of the patents from Exxon is reported here, and what you find here, that again, on a mass basis, okay, and on a volumetric basis, they're very, very similar. That again, the methane selectivity is significantly lower on the iron-based catalyst at these conditions, and that of course, the CO2 difference remains. So iron-based catalysts can be made to work with very high selectivity to C5+, but even at low temperatures still have the CO2 selectivity that for some applications is not reasonable. Let me conclude sort of where I started. What I wanted to know was what was there and what was active. I can tell what is there, because we're able to apply a technique that, in contrast with many others, can actually be applied as the reaction takes place. Even Mossbauer has great difficulties doing that during the reaction. Here we're taking snapshots with about a 1-minute resolution on a reactor that has block flow hydrodynamics, and we can get this information. So we know quite a bit about how much is there at any one point. We have a mechanism for how the promoters work that I think is significantly different than the one that was expected from the chemical promotion that has been attributed to copper and to potassium in this base, iron-based catalyst. Again, to summarize, the surface is all that needs to change, and a few layers in, the contents of oxygen and the structure become largely irrelevant. The promoters act by effectively catalyzing the reduction at individual places and in many places at the same time, so that at the end of the exercise, you end up with smaller crystallites with a higher surface area and a shorter diffusion distance, which takes you faster to the thermodynamically stable carbide without any implications. Again, that is the active phase. This says that we should really be thinking of these surfaces as being dynamic. In other words, it is not a carbide or an oxide. It is a surface that once in a while generates a vacancy on either an oxide or a carbide, and that vacancy then changes as a result of a CO chemisorption, as a result of a hydrogenation of the oxygen and the carbon, and as a result of the desorption of water and CO2. This is all changing as a result of the reaction in the time scale of the reaction. And finally, we can do quite a bit to control the precursors to the point that an iron-based catalyst can be made every bit as active on a per mass or a per volume basis as most of the best cobalt catalysts out there, but even the lower temperature does not buy you a much lower CO2 selectivity. Finally, this work has been supported by the Division of Fossil Energy. I also want to thank Bert Davis for the collaboration that we had had for a while in the area of iron-based catalyst. I will be happy to answer any questions except the one that asked me whether it's a carbide or an oxide that is the active phase for Fischer-Tropsch synthesis.
Thank you very much, Enrique. We'll have time for one question.
Yes, Ed Kugler, West Virginia University. Enrique, this morning you talked about co-feeding water,
Right.
and what effect that had on the performance of cobalt catalysts.
Right.
What happens if you co-feed water under these circumstances?
Some of the selectivity effects that we have seen with cobalt can actually be observed in a much milder way with iron. For example, we can increase the olefin selectivity and decrease the methane slightly by adding water. We have not seen any of the activating effects of water. We have only seen the inhibiting effects of water on iron. My guess the reason for that, Ed, is that we operate a lot closer to the oxidation point for a more base metal like iron than we do for a less base metal than cobalt, and therefore we're already at the ragged edge of the redox chemistry as opposed to far enough removed that we can play with it. But this is a material that has been caught with an identity crisis in between an oxide and a carbide, and is trying to decide what to do with the near surface regions very, very quickly in order to react to any changes in the gas phase. So it's not very exciting. That's why I didn't mention it this morning or today.
Thank you very much.